Hello, my name is Bill Roos, and I'm speaking at the Chapel Implementers and Users Workshop. This is the keynote address. It was supposed to be held in New Orleans, but because of coronavirus, I'm sitting here in my living room. So good morning or good afternoon or whatever time it is where you're watching this. I'm going to be talking to you today about Arkouda, which is an open source package that aims to do interactive supercomputing for data science. So, like many data scientists, I did not receive my formal training as a data scientist. I came up through chemistry. I got a PhD in chemistry, spent a long time doing experimental work there, not even computational chemistry, and then made my way over to data science. So in the course of that journey, I've had many occasions to ask myself, what is data science, and to what extent is it really a science? And I've come to the conclusion that data science really encompasses two related disciplines. One is data science proper, which is the activity of generating a human-level understanding of data sets that are too big to look at with the unaided eye. And then the other is data technology, which are products that are derived from the activity of data science. And data technology is what most people in the general public think of when they hear data science. They think of artificial intelligence, or perhaps in the business world, they think of analytics. But I would argue that data science proper is actually more fundamental than data technology. You can't have good, responsible data technology without doing data science to get yourself a human understanding of the system that you're looking at. Data science proper is also quite difficult. It's underappreciated how difficult it is both to do and to communicate. It's also computationally intensive, which I'll argue in the next few slides. And just in general, it's underemphasized, both by practitioners of data science who tend to almost dismiss this realm of data science proper as just data wrangling or data cleaning, but also by technologists and computationalists who sort of latch on to the artificial intelligence and analytics problems as the more computationally well-defined ones, and kind of don't know what to do with the activity of data science from a computational perspective. And that's what I want to address today in this talk. But first I need to talk more about what that activity of data science proper entails. And really it's the act of understanding the physics of a data set. So what a data scientist might do when trying to gain an understanding of a data set is load in all the data, usually from multiple different sources, join it all together, and then in a single session, as much as possible, the data scientist might take a random walk of this fully connected graph. Now, there are more nodes in this graph than I've depicted here. I just chose some words that kind of nicely encapsulate some of the key concepts in data science. You might summarize the data to generate descriptive statistics. You might filter down to look at interesting subsets or enrich with other data sources. Importantly, a lot of data science involves transforming the data and modeling it or putting it into a framework that helps you answer further questions about the data. Now, this activity has the purpose of generating knowledge. That could be just informal sort of mental pictures of what's going on in the data set. It could also be more formal, like publications or dashboards, or occasionally it could lead to actual data technology, like analytics or a trained machine learning model, for let's say. But not always. It's always some form of knowledge that's your goal. So this process also has many names. It goes by exploratory data analysis, data wrangling, data modeling, data cleaning sometimes. Extract, transform, load is another phrase that captures a lot of this. So there's many names, but it's all sort of aimed at understanding the physics of a data set. So this process has a couple of important characteristics. For one, it demands interactivity. So by interactivity, I mean essentially productivity, but with just enough performance. So in the productivity realm, you can imagine that as you're taking a random walk of this graph, if every time you had to traverse an edge to go from one action to another, you had to recompile your code or make a non-trivial change to your code that involves a lot of boilerplate, or read in data from disk and send it back out again, you're just not going to get anything done, because you might have hundreds or even thousands of these operations in a single data science session. So it needs to be interactive, meaning high productivity, but it also needs to be interactive in the sense that the operations need to complete fast enough that you can stay within your thought loop and not lose your attention span and get bored and forget what you were doing. So for the most part, interactive Python, like Python used inside of a Jupyter notebook or an IPython shell, running on a large server satisfies these criteria for data sets in the small to medium range, up to, say, 10 or 100 gigabytes. So it's worth taking a look at why Python manages to do well in that small to medium case. And for one thing, Python has a reputation for being a slow language. And pure Python, it's true, is pretty slow. But when data scientists use Python, they're not really using Python. It feels like you're writing Python syntax, but if you're using one of the standard data science packages, like pandas or scikit-learn, what you're actually using is Numpy objects, Numpy arrays, and Numpy computational primitives. And Numpy is a package that brings together a bunch of low-level code for things like linear algebra, and this code is written in C or Fortran or sometimes in a GPU language, and it wraps those up in Python objects so that the data science packages that are built on top of it can expose Python syntax, but reach down and actually execute C and Fortran code. So that's what data scientists are typically doing when they're doing this kind of exploratory analysis, is they're using these Python packages that are actually calling C and Fortran code and getting pretty good performance on a single node. But the other thing about data science is that it really demands scaling. It demands scalability. And the reason for that is that exploratory analysis like this, when you're trying to understand the physics of a data set, requires the entire data set. Sometimes for a very few problems, you can sample the data and look at a sample to figure out what you want. But for these large problems, first of all, unbiased sampling is very difficult. And if you have a biased sample, your conclusions are all going to be wrong. But even unbiased sampling has the detriment that it eliminates rare effects and high-order effects. Like if you're analyzing a graph and you want to see a path that spans 2 or 3 or 4 edges, and if you sample that graph, you are going to destroy all of the patterns in there. So this gets to the difference between data science and the physical sciences. In the physical sciences, the assumption is that there is some local physics of the problem that you can learn on a small scale, usually in the laboratory. And then if you want to simulate a large system, you can take that local physics and replicate it out across a mesh or something. But in data science, in general, these large data sets do not have a locality. So they don't have a local physics. The physics are global. And so you have to learn it with the whole data set. And the second point, it should be rather obvious today, is that data sets have outgrown typical computers, by which I mean single nodes, like a server. server memory, is about a terabyte, maybe 2 terabytes. Many data sets, my team of data scientists deals with several data sets that are over 10 terabytes. So we cannot use this single node Python ecosystem to really analyze them. So this kind of leads to a dilemma because interactivity and scaling, you can have one pretty easily, but you can't have both very easily. The single node Python case is where you have a lot of interactivity, a lot of user control and freedom over where the analysis goes and what the computer does. But as we've seen, it gets you only up to a certain ceiling that's not high enough. And then on the lower half of this chart, it's relatively easy to get high power to go fast or to go big. And in fact, the conventional HPC industry has excelled in taking analytics and compiled programs and batch jobs into this realm of high power, of going fast or scaling up big or both. But what data science really needs is high freedom and high power. And so it's interesting. There's a lot of open source projects and interest from industry in taking the sort of single node Python ecosystem and building it out to multiple nodes and seeing if we can get to this upper right quadrant from that direction. To my knowledge, there are not many projects that go from the other direction, that start from an HPC performance approach and try to build up to an interactive user experience. And incidentally, I think this is why data scientists have largely ignored high-performance computing, is because the HPC community does not really have much software that allows you to use a supercomputer interactively. So the analogy here on the screen is HPC builds airliners, and airliners are great for getting a lot of people from point A to point B efficiently and quickly. But what the data scientist needs when exploring one of these large data sets is a fighter jet that the data scientist can pilot individually. So the question is, can we fly an HPC this way? And what that means would be loading terabytes or tens of terabytes of data into a familiar user interface that data scientists already know, that's interactive, where standard data science operations, they execute within the human thought loop and interoperate with HPC libraries that are optimized for the machine. And what we have tried to build here is something that does that. It's called Arkouda, which means bear in Greek. And we think of it as an HPC shell for data science, sort of an interactive front end for a supercomputer. And it's got 3 main design components. It has a back-end server, which is written in Chapel, which I'll talk more about. It has a front-end client written in Python 3 and meant to be used in an interactive setting like a Jupyter notebook. And it has an API and computational primitives patterned after Numpy. So more about that. Remember from the previous diagram, Numpy occupies this trunk position in the Python data science ecosystem, bridging the higher level packages that are composed of Numpy primitives with the lower level implementations that are written in C and Fortran and GPU languages. And so we wanted to do the same thing with Arkouda and to have it be that bridge between, on the lower half, Chapel primitives, where Chapel is handling the parallel distributed computation in an efficient manner, and hopefully one day linking in HPC libraries and maybe even GPU code, bridging that with larger, higher level packages written in Python syntax that compose these Arkouda primitives to do things like scalably manipulate data frames, which are an abstraction for working with tabular data, or do feature extraction for machine learning, or construct graphs or hypergraphs and analyze them. So that is the goal. That's the sort of design principle, design philosophy of Arkouda. Here's a little more about the Arkouda architecture. It has a Python 3 client, as I mentioned, where the user is typing what looks like Python syntax. And that client communicates over a 0MQ socket with a server program that's written in Chapel. And this server program is running on whatever backend platform the user has access to, which can be anything that Chapel runs on, which is really anything. It's from a laptop up to a Cray. The Chapel server has a dispatcher that receives commands from the client and uses that command to figure out what code module to call. And it also comprises a distributed object store, which is what keeps the data around in memory for the user to interact with. And the object store stores block distributed arrays that span the entire platform. So what the server is really a Chapel interpreter. And so I'll take you through at a high level what the Chapel interpreter does for a command. So say the user types in this command, C equals A plus B, where A and B are Arkouda arrays, maybe 100 billion or a trillion element long arrays, and the user wants to add them in an element-wise fashion. So the client code, when it executes, generates this message that basically says, do a binary operation between two vectors. The operation is addition, and the names on the server of these vectors are ID1 and ID2. And in step 2, the module dispatcher peels off the commands and arguments in this command and selects the right code module, in this case the arithmetic module. And then in step 3, it does the argument lookup. It looks up A and B using the names ID1 and ID2, and it allocates the result with the name ID3. And then in step 4, the arithmetic code module does the parallel execution, actually adds the two arrays element-wise, and stores the result in ID3. And then the 5th step, the dispatcher returns the message to the client that says, I created an array called ID3. And then the client knows to create an object called C that stores that information. So meanwhile, the client is handling all the bookkeeping in a higher level sense. And that's done as follows. So A, B, and C are instances of a PD array class, which stands for Parallel Distributed Array. The attributes of this class store the metadata of these arrays. So how big is it? What is its data type? Integer, floating point, Boolean. And I should note that these data types are a subset of Numpy D types, which helps Arkouda to interoperate with Numpy. And it also stores the server-side name that it needs to issue commands. So the methods of this class and the functions that take the class as an argument are what issue the actual server commands over the socket. So for example, overloading this plus operator in Python causes the PD array class to generate that message binopvv that we saw on the last slide. And in particular, deleting an object in the client issues the server command to free the array data on the server. And so this feature and others allow the client language, in this case Python, to handle scoping, garbage collection, reference counting, things like that would be difficult and cumbersome to implement on our own. So why did we choose Chapel for the server-side language? Well, it's really because Chapel has that unique niche in the HPC software ecosystem where it has both productivity, performance, and portability. And the productivity was important for us because really in about the first 9 months of Arkouda's life, it was me and Mike Merrill, who's the inventor and lead developer of Arkouda. It was just the two of us working on it, and we were pretty much working part-time on this, and we had to get something into the hands of our team of data scientists, within a few months. And we could do that with Chapel because, Chapel has a lot of features of productivity languages, but also because parallelism and data locality in Chapel are first-class citizens in the language, and that makes it really much easier to reason about distributed computing, and also more compact to write code. The Arkouda server, even now, after about a year and a half of development, is only 12,000 lines of code, and this is a lot smaller than it would be if we had tried to write it all in C++ with MPI. For the performance, we've run some benchmarks that are available on the GitHub repo that show that the single-threaded performance of Arkouda running on top of Chapel is comparable to Numpy, which is, as I mentioned, using C and Fortran. And the Chapel team has published benchmarks already that show Chapel's scaling and distributed performance is comparable to C with OpenMP and MPI. The portability is a big thing too, because it allows us to develop Arkouda on a laptop and run it on a supercomputer with little or no changes. So that's been really crucial to getting it developed quickly. So here's how Arkouda sort of fits into the ecosystem of big data software that's already out there. To my mind, it's a unique approach. I think maybe there are one or two other packages that start in the HPC land, but from what I can see, there are not many that start with the HPC distributed performance and build towards interactivity. Most packages start with the interactive Python stack or something like it and build it out to multiple nodes. And that's hard to do, but it'll be interesting to see how those packages develop. And it's an open question about which approach is going to be more fruitful. But I think it's good for people to pursue both of them. The advantage of Arkouda's approach is that it really uses the HPC. So Arkouda scales really well to at least 512 nodes, which is the largest system that we've been able to access and test it on. It does so because it exploits the high-speed interconnect, and it also leverages parallel file systems. And it does all of these things without the user having to do any fine-tuning to get it to perform well. So there are some drawbacks, though, of this approach. For one thing, we don't have automatic access to all the features that the Python ecosystem provides so nicely for you. So, for example, we're still waiting on implementing authentication in the Arkouda server. And we only have one I/O format, and that's HDF5. And also, our GPU support is only available on the client side of Arkouda, not the Chapel side. So I want to show you real quick what it looks like to use Arkouda. So starting up is pretty easy. You launch Arkouda just like a normal Chapel program. After you build it, you go into a terminal and you launch it, and all you have to do is tell it how many nodes you want to run on if you're on a distributed system. And it will come back and tell you it's listening on a particular host name and port. And then in your client, let's say a Jupyter notebook, you import the Arkouda Python package, and you say ak.connect to that host name and port. And that's it. Then you're off to the races. So here's a little toy workflow that it uses fake data, but it is sort of representative of one or two of the operations that a data scientist might do when trying to understand the physics of a data set. So the top code block here generates two arrays that are 100 billion long, and each array has random integers between 0 and 9 inclusive. And then it takes the element-wise product of those two arrays and builds a histogram, a 20-bin histogram out of those values in the product. So all that computation happens in about 4 seconds, including the generation of the arrays. And in the bottom block, so that top block is all in Arkouda, and all that computation is happening on the back end in Chapel. In the bottom block, this is all written in Numpy in Python, and so this is being executed on the front end client, and you can't tell the difference, and that's by design. The user should feel like they're just working on a single platform. But one of the things I mentioned earlier in passing is that Arkouda interoperates with Numpy, and that's a big advantage because Numpy and the Python ecosystem have a lot of nice tools for, say, plotting and visualization, and those all work with Numpy arrays. So in this bottom line of code here, you see that hist.toNdArray method that says take an Arkouda array, the histogram, and export it to a Numpy array for use in the matplotlib command that creates a bar chart. So that's what's happening down here. So some more examples of commands that you can do to do interactive data science. And these are commands with timings measured on arrays of 50 billion elements, where each element is a 32-bit value. Now this is real data. This is some data that my team loaded up and had to do an exploration of, and we just measured the timings of our exploration using Arkouda. And we were doing this on a Cray XC40, 96 nodes of that machine. And these are the approximate timings. And so you can see there's input-output. We're reading from HDF5. That takes about a minute for each one of these arrays. And you can do descriptive statistics, which usually involve scalar reductions or histogramming things in a second or so. Also vector operations, arithmetic. Indexing, this sort of logical indexing pattern is interesting. It's imported from MATLAB via Numpy. And what it is the example syntax here says get all the corresponding elements of array A where array B takes on a certain value. This is really useful in analyzing tabular data, and this again executes pretty fast. You can do set membership, gathers. Gathers are kind of variable because if the index vector has a lot of repeated values, it'll cause hotspots in the network. But if it's just a permutation of the array, it also goes quite fast in a few seconds. You can look at individual items. And then these bottom three are really important. You can sort arrays and also sort the indices of an array by the values in the array. And for one of these 50 billion long arrays, it takes about 15 seconds. And that is insensitive to the distribution of the data, as I'll explain in a minute. And then from there, you can also group arrays by value. So this is a familiar operation to data scientists, and usually what you want to do when you group an array by value is aggregate the values of some other array by the values of the array that you grouped on. And so those operations also are pretty fast. They're not instantaneous, but they're under a minute for these 50 billion long arrays. And these are the important ones where that require a fast interconnect and efficient use of it. So more on that. Sorting is critical because it's the rate limiting step in most of the higher level Arkouda workflows that at least the people on our team use. So sorting comes in sort of two flavors. There's argsort, which again is sorting the indices of an array by the value of the array. And then coargsort, which does the same thing, but for multiple arrays in conjunction. Numpy has something similar called lexsort, but it's kind of backwards of the way we wanted to do it. But these sorting and coargsorting routines underlie things like taking tabular data and grouping by one or more columns. This is hugely common operation in data science. Creating sparse matrices, finding unique values, reindexing a sparse value into a dense range, extracting features for statistical testing or even machine learning, and computing set operations, to name a few things. Arkouda, for its sort, uses a least significant digit radix sort, which is a sort that requires a fast interconnect because at every step it's doing ON communication. And so W is the number of digits in the range of values, the number of digits in the range of values. And so for each digit, it has to do big O of n communication. So it requires a fast interconnect, but if you have one, the runtime of this sort is independent of the data distribution. The best case, the worst case, and the average case are all big O of Wn, and so you know exactly how long your sort is going to take before you run it, which is really nice for the user, not to be sort of sitting there wondering if they've just hung their machine. But the other thing is that I haven't put on the slide here is that the radix sort is really easy to parallelize. It comes in at about 1 or 200 lines of code, I think, even for the optimized version. And so it's got very low overhead and it scales really nicely. Speaking of which, here's the scaling behavior on a Cray XC with an Aries interconnect. So the scaling is pretty linear up to 512 nodes, which is the biggest biggest system we've been able to run it on. If we had access to a bigger one, I bet it would scale higher. But that performance is also portable to InfiniBand. It didn't used to be, but Elliot Ronahan, who generated these scaling plots and did these measurements, is going to talk in the next talk about some of the great work that he's done to make this portable to InfiniBand networks. So I wanted to show you an example of Arkouda serving as this sort of trunk between the roots and the leaves, like we had designed it to. So in a previous slide, I mentioned computing set operations. Well, back in the single node Python ecosystem, Numpy allows you to compute set operations, treating Numpy arrays as sets. And you can do things like take the intersection or the union or the set difference. We wanted to do the same thing in Arkouda, and with the Arkouda primitives that we have that execute on the Chapel backend server, we're able to follow NumPy's lead and compose those primitives into a relatively compact implementation of these set operations. So I've shown here the actual Arkouda source code for doing set intersection. And after the sort of argument validation, you can see it uses things like unique, concatenate, argsort. These are all Arkouda primitives that execute on the Chapel server. But it's written. This function looks like it's written just in Python code. And it allows you to do efficient set intersection on these 50 billion long arrays or more. And it's very similar to the NumPy implementation of the set intersection. So I think this is kind of the principle of composability that has really allowed the users on our team of data scientists to take the Arkouda primitives and really make them into more complex, higher level operations on graphs and data frames that we never really thought, never really expected them to do at first. It's been more successful than we had even hoped. So where we would like to go from here is we would like to improve in all aspects of this ecosystem here. In terms of higher level packages, we would like to implement actual data frames. There's a package in the Python ecosystem called pandas, which exposes this abstraction of a data frame, which is basically a large Excel spreadsheet, a way of manipulating tabular data. And it would be really useful to replicate some of that functionality out of Arkouda primitives. We also want to build out sparse linear algebra in terms of Arkouda primitives. In Arkouda proper, I mentioned we are adding authentication and basically in general making it safe for use in a multi-user environment, beyond just our team of users. Also we are adding data sharing and access control capabilities and thinking about how we might go towards multi-user resource management. So Numpy, because it lives in the Python ecosystem, gets to use all of the nice operating system architecture around supporting the Python process and shared memory, things like that. We don't get to use all that. Adding this kind of resource management for a multi-user context is a challenge. And then in the roots, in the lower level sections of this project, our dream really is to take some of the optimized HPC codes that are out there in industry and in academia and link them in to Arkouda so that users can call them from Python, driving an HPC interactively. So things like Fourier transforms, tensor decompositions, eigensolvers, graph analytic and hypergraph analytic techniques, basically anything that can interface with Arkouda and Chapel, really. So there are toy examples of linking in HPC like MPI codes with Chapel, but what's really needed is for the HPC community to standardize on a distributed array interface for passing data back and forth between these packages and Arkouda. And that's really a large part of the success of Numpy, is that Numpy has created this actual standard called array interface, which allows it to use C and Fortran arrays and expose them to Python, and all the developers on either side of that divide know exactly what the data should look like. So that's what we need to do with the HPC community to enable that. So in closing, I'll just note that what we've got here is a new but really an old perspective on what an HPC should be. So my collaborator who I've mentioned, Mike Merrill, he's been in the HPC community for some 32 years, and he tells me that back in the 90s or so, a supercomputer really was a single-user kind of interactive platform. And it wasn't until the 2000s that HPC became really a batch-oriented, job scheduling compiled program thing. And so what we're advocating is that keep that application of it, because that's very useful. Airliners have a big role in today's economy, but we also need fighter jets, because you can't do, for example, cybersecurity. You can't defend your airspace with a 747. You need something like an F-22. So with that, I would like to acknowledge Mike Merrill, who I've already mentioned several times, but he is the inventor of Arkouda and the lead developer. And he and I were working on it together for most of the early months of Arkouda's development. More recently, in the last 6 or 9 months, Elliot Ronahan has made a lot of really significant contributions in the performance, especially of sorting. And he's going to present some of that work next talk. It's really impressive. And also the Chapel team, the whole Chapel team has really been instrumental in helping us to use Chapel to the fullest. And I'd also like to thank everyone who has contributed to Arkouda. As I mentioned, it's an open source project, so please check us out on GitHub and maybe become a contributor. So with that, thank you very much for your attention. If you're watching the Chapel Implementers and Users Workshop Live. There will be a Q&A after this talk. If not, thank you, and I'll see you later.